Hey guys, my name is Adrian and welcome to Organic Chemistry 2, Part 10 of these recorded sessions. So today we're going to go over for most of y'all Chapter 22 and in general carboxylic acid derivatives. So we've been talking a lot about carboxylic acid derivatives and now they're getting their own chapter pretty much, right? So um, again, we'll do the review. You can do whatever you want with the questions. 20 questions still, so take it. And if you want to go over it with me, go through the video, things like that. Or if you just want to take screenshots and then do it later, um, then come back, feel free. So pretty much whatever strategy you're using, whatever is working for you, great. Um, but either way, right, you have questions to practice with, things like that. And just about this chapter, um, it's one of those chapters that's very. These last three chapters pretty much are very forgiving in the sense of that um, they're eas they're easily like separated, or you can break down the topics easily, so it's not confusing. And depending on who you have, who your professor is, um, if you have lectures or PowerPoints, things like that, it's pretty much blocked out for you. So it's kind of, each derivative has its own thing, and then that's all, right? So, and as always, I always say that my study strategy is always like breaking them down into like their own categories. So that's what's good about these chapters because they all have their own categories. So with that being said, let's get started and let's see what you guys have. Okay, as always, pause the video. You know, do your thing. One, you guys should have gone. So we're looking for a lactam, right? So this one, you guys should have gone A, right? And then again, I always say that with these questions, you can, um, you know, kind of twist them, ask whatever the opposite of what they're asking for is. So in this case, we look for the lactam, right? What about lactone? Are any of these lactone? If not, then draw it out. If it one of them are, then which one? So lactone is actually not in this one, but has a general formula like this, right? So it has this additional oxygen, right? So things like that, kind of keep adding on. And since we're learning about new derivatives, things like that, new functional groups, right? Um, we're gonna run into naming. So as always, so in this case, IUPAC name for this compound. This one you guys should have gotten D, right? And this one is obviously a what? An amide, right? And then we know that amide, we just pretty much name um, one side of the nitrogen and then the other side, right? So in this case, let's do this one since I think the next one is pretty much similar. So let's just do this one. So where did I get this from? So we have the methyl group, right? The methyl group is right here, so that's there. N-methyl, and then butanamide. Butan is four. So that means one, two, three, four, and we have three methyl, right? Methyl. So that's where they get that from. And butanamide because it's four carbons, butan, right? And then the amide, obviously an amide derivative, right? Okay. Three, acetic propionic acid. Um, so this one you guys should have gone A. So this one we've seen this a lot, right? We know what the propio structure is. We know what the acetic structure is, and we just combine them. So and this time it's an anhydride instead of an amide, right? And again, you have these structures, right? And you can probably name them. And pretty much all of these are just different um, versions, right? So which one of these is propio? This one's the propio part. This one's the um, acetic part, right? Acet. Right? So not too bad. Don't forget those common names. Don't forget those especially with carboxylic acid. We learned in the past. We have the formic, acidic, propio, butyr, valeric, capro, right? Don't forget those. Four, and as always, new derivatives, new functional groups means going back into a little bit of spectroscopy. So that's what this is about. Whereas the carbon absorption in the IR, and those are one of the famous ones, right? Carbonyls, so you should get D. And by this time, hopefully, you guys know where some of the common IR functional groups are, right? So in this case, we know carbonyls are always going to be around 1600, right? Okay, so now, oh, we have one more. 5, your skin absorption 2250 in the IR compound. What kind of functional group is this? So this one, you guys should have gotten D, right? Because for sure, not a ketone or an aldehyde, right? Because ketones and aldehyde did see the carbonyl. So that'd be in 1700, like number 4. Now we're down to ester and nitrile. So ester, where would that fall compared to the nitrile, right? So ester is similar to carbonyls. It's in the 1700s, while nitriles are in the 2200s. So yeah. So don't, if you forgot, review, because um, depending on your professor, you may not or may get the chart again, right, for this test, for this upcoming test or whatever. So be wary of that. Okay, let's go to the next page. Okay, so pause the video, take notes, do what you will, and come back. Okay, 6, you guys should have gotten D, and why D? So again, we're talking about spectroscopy. How do you tackle this? So we've seen a lot of different questions kind of asking the same thing, but in different point of views, right? Different ways. So this is one of them. Um, we know for sure the chart is telling us there's 3 environments, right? So basically, one by one, let's see which one of these have 3 environments. So for A, ethyl acetate, we have something like this, and then 2-propanone, just a ketone, and then C,3,3-dimethyl 2-pentanone, and then D, we have this, right? So let me get a color out, and let's see. So first one, we have how many hydrogens? 1, 2, 3. So far, so good. We have this one, 1, so we can cross that out. This one, 1, 2, 3, 4. So this one's out. So B and C are out. 1, 2, 3. So now we're down to A and D. So now how do we differentiate this? Well, this we could use the ratio. It'll be really easy because there's there's an apparent 9 hydrogen ratio right there. So where do we get 9 hydrogens in one environment? This one, right? One environment, 9 hydrogens. So that's why we chose D. Okay, go back to the normal. And hopefully you guys are used to these questions as well, because pretty much you know, these will keep coming back, right? So, okay, 7. Why doesn't nucleophilic acyl substitution stop at the tetrahedral intermediate? So, this one, you guys should have gotten B. Reforming the carbonyl is energetically favorable because what's the steps? Our first step is a nucleophilic attack, right? And our second is the leaving group elimination. And so basically this is saying um basically saying tetrahedral intermediate. So pretty much you're going through something like this, right? I do that too. So we have a nucleophile. It's gonna attack. We go there. We end up with this product over here, right? We have this is the intermediate. But what it's saying is um, it's reforming the carbonyl because we have a leaving group right here, right? So basically, that halogen is a good leaving group, so it's not going to stay this way, so it's going to keep going, right? So that's why 7 is reforming the carbonyl. So in this case, you kind of need to do a little bit of digging, right? So the best thing to do is, okay, what happens in a nucleophilic acyl substitution, right? And for sure, the leaving group is not unstable because it's a halogen, right? Obviously, it's going to be the best leaving group, so C is definitely wrong. There's no intermediate. Well, there is an intermediate. We just did it, right? So C and D for sure wrong. Nucleophile is too basic. Um, this one is wrong because it's not because it's um, too basic or anything like that, but because it doesn't matter. It's going to go through the substitution still, right? So let's go to 8. Why is pyridine included in the reaction of an acid chloride and an amine or alcohol? So this one should be B, right? And this one is one of those questions that it's not just specific to pyridine. It can be applied to other reactions. And basically, usually you have reactions that's like this, right? So your main reagent or whatever. So main, and then you have randos over here, right? So basically, I like to call these kind of like spectator. They do stuff, but they don't do the main reaction, right? Unless it's like 1, 2. But usually, if it's not, if there's no, if it's only one reaction, these bottom ones here are just random, like H2O or whatever, right? So those are kind of just like what D says, neutralizes, they stabilize, right? I call them a spectator because they kind of just watch and make sure things go right. Stabilizes. So that's what I like to call them. But yeah, again, this applies to anything, not just pyridine. So it's not really pyridine specific, right? Okay, so next page. Okay, again, pause the video, screenshot, answer, do what you will, and come back. Okay, 9, you guys should have gone B. So this one, it's not, you kind of have to this is where the blocked topics are for different um, groups. So what groups are we dealing with? We're dealing with what? Acid chloride going to, in this case, with this reagent, right, they gave us, basically this one, we're going to end up with an anhydride. So which one of these are anhydrides? Um, so for sure, well, actually, there's a couple, right? So for sure, B and D are anhydrides, right? Four, one definitely not, right? Three, not really, because it's just a dicarbono, right? So now we choose between 2 and 4 and what's happening between the reaction, right? So basically, we know that this group over here is just going to attach where that leaving group leaves. So that's why it's not 4, right? So this could be mistaken as, well, actually, no, 4 is definitely wrong, right? Where are we getting that other benzo group? So, but once again, like 3 chapters per test type thing, right? For most of y'all, right? So once I start mixing things up, you might get confused by other reactions that we haven't covered yet. But in this case, as of right now, it's definitely not 4, right? So, okay. 10, how can you convert carboxylic acid to acid chloride? So it's, again, pretty much same question, different in a different way, right? So carboxylic acid into an acid chloride, right? So this is basically what it's asking, right? So what's the reagent here? So this one, you guys should have gone B because that's that certain reagent will make acid chlorides from carboxylic acids, right? And that's just one of those things you have to know. Um, and again, you can go a step further. So what would we get if we did hydrochloric acid? What would we get if we used um, halogenation, right, with the chlorine or sodium chloride, things like that? And you may get a reaction, you may not. So you just need to pretty much go through the list, and actually the list will be going over after this, the summary. So just go through look through that list and see, okay, is this even possible? Okay. 11, what is the direct product of base promoted hydrolysis of an ester? So this one, you guys should have gotten D, carboxylic acid salt. So again, um, in the reactions, you'll have acid catalyzed, base catalyzed. So watch out for those. Pretty much base catalyzed. So acid catalyzed and acid, right? You'll pretty much be getting a carboxylic acid. I almost said skillet. Carboxylic acid, right? Base catalyzed are usually always um, they'll have an intermediate, or yeah, you have the salt, which is that anion, right? So negative charge. So just kind of like a general rule, because there's going to be a lot of acid catalyzed, base catalyzed, and the connection with those reactions is because acid catalyzed always goes all the way to carboxylic acid, while base catalyzed stop at the salt. And that's just one of those things that um, that are the same for everything, pretty much. Okay. What do okay, 12. Where 12? 12. What reagent would you use for the following reaction? So CN going to CHO. So an aldehyde, right? So this is a what type of reaction? Reduction, right? So you guys should have gone B, Dival, and we've seen Dival a few times, a lot of times in the past, so should be no surprise. Lithium um, is to it's gonna reduce it to an amine, not a carboxylic acid, right? So H4 will reduce it to an amine. NABH, same thing. It's strong, right? I guess I'm gonna do and NABH4, and then PDC is also a reducer, right? But it's a weak one. Okay. And again, if well, most of you probably already have your notes, right? Um, and hopefully you guys notice that some derivatives can make other derivatives, while other derivatives cannot make other derivatives, right? So hopefully you're connecting that dots because obviously carboxylic acid can't go to carboxylic acid, right? So that type of thing. So certain derivatives can only make certain derivatives. So make note of that, and hopefully you guys catch that. Okay. 13. What is the IUPAC name of the following compound? So this one you guys should have gone B, phenylpropanoate. So now we're into esters, right? 8 is esters. 8, and pretty much we have a phenyl group, and propanoate, the propio group, right? So nothing's crazy. Okay, let's go to the next page. 14. Okay, you know, pause the video, screenshot, do whatever. 14, you guys should have gone A. And again, for this one, you're going from a nitrile to a what? So we have an acid, right? So this is with an acid workup. So, oops, hydrolysis. So this is the reaction you're going for. And this nitrile hydrolysis actually makes, speaking of, derivatives making other derivatives, this is going to make carboxylic acid. So, but if we had a base, so this is the with the acid, but if we had a base, what would it make? The carboxylate anion, right? So RCOO minus. So again, that's what I was telling you with the acid and the base. So in this case, it was A because it went all the way to carboxylic acid. But if we had base, what answer choice would that have been? That have been C, right? So answer choice C is the base. So things like that, go further and see if any of these choices make sense with other reagents or combinations of whatever, right? 15, following product of SOCl2. This one we just did, right? SOCl2. So this one you guys should have gone what? D. It pretty much stays the same. OH turns into Cl. So this one is pretty much just halogenation. We've seen tons of it before, right? So nothing special. I feel like I'm squinting too much, am I? Okay. Hopefully the glare in my glasses, well actually that will be even worse. Um, but hopefully I'm not squinting too much, or hopefully there's not too much glare. Okay. 16, which of the following conditions can be used to synthesize an ester? So now, again, this is a different way of asking the same question. So pretty much we're looking for the product and the reagents. I mean the reactants and the reagents to make ester, right? So 16, you guys should have gone B. And again, meaning that you can get an ester from a carboxylic acid, right? We started with a carboxylic acid here for B with an ROH group plus hydrogen to make that ester. So nothing crazy. And you can even try with the other ones because for sure for ester this we needed this for sure, the ROH for ester. So C and D could be choices as well. But C, instead of an acid, we have a base. So that's not going to make an ester. Um, and in D, it's missing, well, actually, it's actually from an amide, right? So an amide won't make an ester because it has an amide. It has a nitrogen, right? Okay. And actually over here, let's see. Let me just do this one. So A, if we did A, you couldn't have um because of the amide or the amine in this case. C, you would have made a carboxylic acid, and same with D, you would have made a carboxylic acid as well, right? So okay, 17. Draw the structure for N-phenylacetamide. So N-phenyl and then acetamide group. You guys should have gone 3, right? C. So this one's kind of like naming but backwards, right? So they gave us the name, but we're looking for the structure. So this one, well, actually, no, we kind of already went through that, right? We have our phenyl group, and then we have our acetic group, right? So 18 from the list below, pick the compound that does not react with acetyl chloride. So again, this is D, but again, hopefully you guys are connecting the dots. Like acetyl chloride works with isopropyl alcohols, azotic acid, ammonia, but now with triazoamine. So if it was A, you would make esters, right? B gives you anhydride, and C will give you primary amide. So acetyl chloride can react with A, B, and C to provide esters, anhydride, and amide. And triethylamine does not have hydrogens, right? So it's not going to make anything. It's not even going to react. Okay. Let's go to the last page, I think. Okay. So now, lots of questions. And again, I don't know if I've mentioned this before, but concept questions are pretty much like the drawing questions, but in word form, right? So take a second, take a minute, pause the video, and tell me what you guys got. 19, N-butane nitrile will undergo all of the following listed reactions except for one, which is not true for N-butane nitrile. You guys should have gone B because, again, some reactions are specific to different derivatives. So, and in this case, actually, you can just follow what they're saying. For A, ethyl magnesium bromide, obviously that's Grignard, right? To form an alcohol. So that's true, obviously, because we know Grignard reagents make alcohol. C, let me write this down. A is the Grignard, which is true, right, to make alcohol. C, butane nitrile is hydrolyzed in the process of acid to form butanoic acid. True, because with acids, we always get the carboxylic acid derivative, right? So acid workup, I'm just gonna say workup because okay. And it reduced with phenol H to perform butanol, right? Which makes sense. And butanol is pretty much yeah, and butanol pretty much we kind of saw that earlier, nitrile to amide, right? The nitrile to amide. So that works. Okay. So that's why. And now for 20, all the following contains sp2, and this one's just a throwback to hybridization again, right? Since we have new derivatives, new functional groups, we're just visiting old concepts that hopefully we haven't forgotten, right? And obviously this one is a B because it's a triple bond, right? And this is sp2, sp, and everything else here, carboxylic acid, sp2, aldehyde, and hydride, they're both sp2s, right? Okay, so that's it with the review. Nothing too crazy, right? Pretty much, pretty straightforward, except for the fact that you know, in this chapter, even though again, like they're neatly organized for you, there is a little bit of memorization involved, a little kind of like newer stuff to kind of learn. So let's see, and we'll get to them. Okay, so first things first, let's do a little bit of summary for carboxylic acids. Acids. So the derivatives, right? We have our carboxylic acid, right? Which is given. We have our acid chloride, right? And we already know how to name carboxylic acids, but for acid chlorides, we name it if it's an acyclic. We name it ill chloride, right? Fair enough. If it's cyclic, we name it carbonyl chloride, right? So pretty straightforward. Whatever. 3-anhydride, right? Um, Also naming it if it's symmetrical, and I think we did some of this earlier, or one or two. We just end it with anhydride. Of course, we name what the groups are on either ends, right? Mixed, we name it same thing, but we alphabetize it. So I don't know why I put quotation marks, but they're alphabetized. So alphabetized. So if one group is like acetic and one is a propanoic or whatever, right? Propioic or whatever. So you'll name the acetic first. 4, we have esters, right? And we know esters. 8, 5, we have amides. So primary amides, or just amide, and this is what we saw earlier with the N-amides, right? N, N, right? And this is just the general, whatever that group is. Maybe I should have put R, R. But, and then last but not least, nitriles. And nitriles are a funny one because obviously they're not a carboxylic acid derivative because they don't have like the double bonded things like that. But they're one of these because they can make carboxylic acids. So 6, 5. Okay, yeah, I'll have enough room for the other one. So alkane, just a regular straight chain, right? Just nitrile, whatever nitrile, right? And then if it's a common name, actually same thing, alkane and common name, and with nitrile, right? So now I mentioned a couple times before that there's priority groups, right? Of like naming of reactions, of whatever. So now you guys kind of get to see that. So the increasing stability is, let's see, acid chloride is less stable than anhydrides, and then carboxylic acids, then esters. Actually, esters and carboxylic acids are about the same. And then amides are the best ones of them all. Okay, so let me color this. This is the increasing stability by resonance. Stability by resonance. Okay, right. And we know that, let's see, I think I have one more here. Basically, the more basic, the more stable, right? So that's what that's saying. So obviously, amides are the best, more stable, and more basic. That's what it's saying, right? So kind of connect the dots. But yeah, this is what we're all going to be talking about, and each of these has their own little sets of reactions. So let's get started with um. Actually, before that, let's talk about the reactions they'll be going under. Nucleophilic acyl substitution. So we said nucleophilic attack first, and then I'm going to do this so we save room. And then second is the leaving group elimination, right? So this is pretty much going to be the base of every reaction we'll be going over to from now. So with this one, obviously we know nucleophiles are, you know, negatively charged, the best ones, things like that. And this is kind of just the order. So since we're pretty much familiar with them, I'm not gonna redo them, but again, this is kind of the order, right? So NH2 is the least, OH minus, OR, and it's the same with OH and OR. RCOO plus, then Cl minus, right? Which is pretty much halogens. So this is increasing leaving group ability, reactivity. right? And we kind of know that because we know for sure NH2 is the worst leaving group. It never leaves. OH is the same. Same with OR, and then the best ones are the halogens, right? So that shouldn't be a surprise. Okay, so the main thing for that one is this, right? Okay, so now let's put this to the test for each derivative, right? So first things first, carboxylic acid. So let's do it like this. There's four reactions we're going to be talking about. Oh, actually there's a five, but it's not part of this. It's like an additional one, but we'll have room. So we saw SOCl2, ROH. What do you guys think that that be, right? NH3 and heat, and then RNH2 with okay. So first one, we'll make an acid chloride. Second one, we'll make an ester. And let me put it there, right? Um, Next, we'll make an amide. And next, we'll make NHR, a secondary amide. So we kind of noticed that these are both amides, but this is primary, this is secondary, right? And then esters. So this is what carboxylic acid can make, right? So the questions from the review that's asking, um, it wasn't about carboxylic acids or anything like that, but it's the same concept for the other derivatives. When it was asking, basically, can this turn into an ester, right? And then the thing that I didn't make space for, so I'm gonna have to write it up here, is this dicarboxylic acid can make a cyclic anhydride. So pretty much like that, right? So that's that as well. So pretty much, and something that's special about this is this one's called esterification, Fischer esterification, Fischer esterification, right? So that's pretty much it. But other than that, there's not really any specific names for any of these. It's just, um, yeah, carboxylic acid reactions turning into primary or secondary amides, esters, acid chlorides, or cyclic anhydride. Okay, so that's that, right? So actually, let me. I want to emphasize this, so I'm gonna add them. So cyclic anhydride, acid chloride, ester, primary amide, secondary, right? So from carboxylic acid. So carboxylic acid can turn into any one of these. So now let's move on to our next target, acid chlorides. So this one has two separate ones. So let me make sure to account for room. Okay. And then let me do this one as well. Okay. So, first things first, we have the carboxylate anion, right? And we have H2O, and then pyridine, right, from the question. And then we have ROH and pyridine as well. So this one we end up with an anhydride, right? And we'll specify that later. This one just an carboxylic acid, and this one an ester. Now this one we have, this one's interesting, and I'll explain it to you. NH3, 2 equivalent, or NH2, 2 equivalent, R2, NH2 equivalent. And pretty much they go to the primary, secondary, and tertiary amide. NHR. So let's finish drawing them just for consistency's sake, right? Okay. And why is 2 equivalent being used is because these amides here, they act as both the nucleophile and the base at the same time. So you have two of them because one of them acts as the nucleophile and the base, right? So yeah, and you must have 2 equivalent. That's the thing about these. And let's keep it consistent with the green. So acid chlorides, right? Acid chlorides can turn into um, anhydrides, carboxylic acids, esters, primary amide, secondary amide. And you notice how carboxylic acid didn't get turned into tertiary amide, right? But this one did. So, right. And again, 2 equivalent, 2 equivalent, 2 equivalent. Okay, so that's it for acid chloride. So I just realized I haven't been saving these things. I feel like I should have, but oh well. Okay. Oh, what was it? So now we have anhydrides. So this one, instead of the acyl substitution that we've kind of been doing, this one is kind of a little bit different. We have the nucleophilic attack as always. Second, we have the leaving group elimination. So same. And then, but this time we have protonation. And again, let's do this. And this one doesn't have many, so that's good. So let's start with that anhydride. H2O, ROH, NH3, 2 equivalent, right? Pretty much the amides that are reagents are going to have equivalents. There, carboxylic acid. So, and you're kind of sensing a pattern here, right? We've used ROH for pretty much all esterification. So H2. Okay, so let's just name them. I'm trying to emphasize it because you know you definitely need to know that anhydrides can only turn into carboxylic acid, esters, and what? A primary amide. So if you get a question something like, can anhydrides turn into tertiary amides? No, right? For carb acids, esters, primary amide, right? That's what they can turn into. Okay, so we're moving along pretty quick, which is good. Now let's go to esters. So this one's interesting one because esters can be used for so many things, and they just apply to a lot of things, and in biochem especially. So we'll talk about that later. So now esters. Okay, H2O acid, H2O base, and then any kind of amine. Oh, let's see. Amine. Okay, so with H2O and acid, like we said, turns to carboxylic acid directly. This one turns into carboxylate anion, and this one turns into um, NH or NR, whichever, right? Doesn't matter. So, and actually, this one can react with an acid, a strong acid, and go all the way to carb carboxylic acid, right? So it can still go to carboxylic acid. It just needs more, a little bit more push, because right now this is like the intermediate, pretty much, right? So carb acids, um, carboxylates, I guess we'll call it, and then this one's just any amides, primary, tertiary, secondary, right? And now with the relation to biochem, it's relevant in lipid hydrolysis, right? And you'll see these. We're not going to get into it too much, but you'll see tags in biochem and lipases. Tags especially because that's like triacylglycerols, right? Which is pretty much long chains of esters. And then um, soap formation. So soaps are fats, right? Which these are, so or which lipid is, right? So that's why it's important. So hydrolysis, and then it's called saponification. You might or might not um, encounter saponification, but it's pretty much how to make soap. How to make soap. Okay, so that's that. Fun info. Now let's go to amides. And this one has a lot actually. And actually, yeah, let's do two. So amides, H2O acid, H2O base. So what do you guys think will happen? Right? Same thing as what happened to the esters. We'll get carboxylic acids with the H2O and acid, and then the carboxylate anion, right? Again, for that carboxylate anion, we can go through again to make the carboxylic acid, right? Okay, but let me name these because um, something interesting is there's an exception, not an exception, but more of like a caveat with these that that the esters didn't have. So acids, carboxylate. So this these have intermediates. So, or I guess no, not intermediates, byproducts. So additional products. So this one will end up with a ammonium, right? And this one will end up with an amine byproduct. So byproducts. So that's the difference between those as well. So carboxylates with amines, carboxylic acids with ammonium, right? So now let's go to the fun part. This one, like, you wouldn't think so, but this one actually has a lot of reactions for being so weird because it's not really a derivative, but it makes it so. Nitriles. And how do we make nitriles? Rx plus Cn SN2, we get RCN, nitrile. So, let's see, how many is this? 5? 3, 4, 5. Okay, so first, as always, with acid, H2 with base, LiAlH4 with water. So, yeah, we saw this all over the review, right? I think we saw more of these than the other ones, actually. And then MgX for RLi H2O, right? So this one, carboxylic acid again, right? No surprise there. This one, carboxylate anion, no surprise there. Lithium will reduce it, right, like we said, to an amine. Right? Or actually, amine, not amide. So, let me erase that. Okay, there we go. NH2, H2, right? Oh, I guess I'll put the R there. Dibal H makes an aldehyde, right? Um, and then this adds the R group, as we know. Okay, so again, let's name these. So not too bad, right? Pretty much a lot of these just repeat over and over, so that's good for us. It's always good when they repeat, because then we don't have to keep studying. We don't have to, um, you know, learn new stuff, technically, right? That kind of sounds bad, but it's okay. Okay, okay. So now, in addition to this, nitriles also have like something a little bit more special, but not really because we've seen it before. But this time with nitrogen. So tautomers. You can have let's see, let me try to fit it. Imidic amide tautomers, right? Like keto, we have imidic amide, and let's go to keto. Oh, actually, yeah, let's do keto, as well, just to review. But how do we get it? OH, right? And again, it's gonna favor this one, this product. And why does it favor this product? Because this CO bond is better, right? It's more stable. And then the regular ketoenol, so we start with the ketone, which is the more favored product, and go to the enol. Right? And if you think about it, the amide is the keto version, right? While the imide or imidic is the enol version. So, food for thought, right? So, with that being said, that's all I have for you guys. Nothing too crazy, right? Again, those categories of derivatives made it so easy, made it so very, I guess, very manageable, right? It wasn't just like a huge dump of reactions, but we actually got to be able to separate them, have their own categories, things like that. So it was like nice bite-sized pieces all around. So with that being said, that's all I have for you guys. We're almost done, and hopefully you guys stick around for the last couple sessions. Hope to see you guys next time. Bye.